The outer two most planets are Uranus and Neptune, and both of them appear blue. I mean, these pictures don't necessarily do them justice. They're really kind of the same blue color there, but they're both gas giants, but they're smaller and they're much colder. So sometimes they're also referred to as gas. As ice giants. Sometimes what they're referred to, just to differentiate them a little bit from Jupiter and Saturn. In the end, they're all fundamentally still kind of the same idea. They're just colder. And so whereas Jupiter and Saturn have still a lot of molecular and metallic hydrogen that's hanging out and a little bit more latent heat, these guys are certainly colder and smaller than Jupiter and Saturn, still much bigger than Earth, but they're still the fundamentals are still the same there. Now, Uranus and Neptune, they weren't known to ancient astronomers. They were actually fairly recent discoveries as far as things are concerned in our sky. Uranus was discovered in 1781, and Neptune was actually initially predicted to have existed. They tracked Uranus's orbit for a couple dozen years, basically one orbit of Uranus, and predicted that there was actually another planet out there that was kind of causing little perturbations or causing little fluctuations in Uranus's orbit, and they predicted where Neptune was and then found it. So in 1846, they found Neptune. We'll talk about one of the big asteroids closer to us. Ceres was actually discovered before Neptune was. So there was a point where we knew about a few asteroids in the asteroid belt before we knew anything about the furthest planet, Neptune here. Now, Uranus and Neptune are basically the same size. So there is far less differences between Uranus and Neptune than there are Jupiter and Saturn. Jupiter and Saturn, there's their size difference and such is significant enough that there is some more differences there. But Uranus and Neptune are basically the same size. They are both significantly smaller or less massive than Jupiter and Saturn. They're about 15 Earth masses, so they're about a 20th the mass or so of Jupiter, and about a sixth of the mass of Saturn. They're about 5 times the radius of Earth, but they're significantly smaller there. And Neptune is just a touch more massive. Neptune's like 17 Earth masses. Uranus is like 14. There is a slight difference there, and it compresses it a little bit more. The more mass compresses it and actually makes it a little bit smaller, because you actually can have a little bit more compression where you get more ice, in addition to it being colder and so on. But we'll say that we'll talk about that in a couple slides here. But the compression allows more of the molecules to basically turn into ice, and they'll actually take up less space than when they were kind of in that gaseous form on the outside. And broadly speaking, whenever we talk about ices and rocks, particularly that difference there between these solids, right? So the ice and rock are both elements kind of in their solid state, and rock usually deals with things that are rocks and metals, typically heavier elements. So silicates, your metals, magnesium, iron, and so on, they all will form broadly rock. And these are all materials that typically are not, they're typically solid at most temperatures in space. So we don't really ever find molten iron or molten silicon or molten rock kind of like free floating in space, but we do find vapors from oxygen products or from carbon products or hydrogen, of course, being most plentiful out there. So ices are basically the solids that are formed from volatile materials, or materials that otherwise might just be a gas in open space. So hydrogen, oxygen, nitrogen, they all can form different compounds that are volatile, because in space we can see them actually in multiple different forms. So just like in Uranus and Neptune here, the put them in under enough compression, and they turn actually into a solid. Typically in space, we don't find liquids unless there is an atmosphere. Liquids, you have to have kind of a surface and some pressure to apply consistently to have a liquid. So in the depths of space, really, we only ever talk about gases and solids, and the solids of hydrogen compounds or of any sort of volatile compound would just be referred to as an ice. But when we talk about ice, this type of ice is probably as hard as any stone that you would find on Earth. We're not just talking about ice you could probably chip away at with a shovel or something. We're talking about ice you would need a nice reinforced jackhammer or pickaxe to actually do anything to, just like you would have to chip away at stone at a quarry or something. That this ice is extremely dense, extremely cold, extremely solid, that thinking of it as just ice out of your refrigerator doesn't quite do it justice. But the difference here is just what they're made of. And as we saw with Jupiter and Saturn, the rock portion is all in the very interior. It's that pit of the planet again. And then it's the next densest thing is on the outside. Now, Uranus and Neptune do not have a layer of molecular hydrogen for a few reasons. One, they probably don't have enough interior heat to maintain hydrogen in that state. Jupiter and Saturn are massive enough. They have a lot of retained energy on the inside that probably helps to keep that material there in that state. In addition, Jupiter and Saturn are 10 to 20 times more massive almost than these guys. They have a lot more pressure to compress that hydrogen into a totally different state. Whereas here, they just don't quite have the mass. They don't quite have the gravity to turn all the hydrogen into that unique state. So they're a little bit more a normal kind of ice, if you want to think of it that way. It's not as exotic. And maybe calling this ice is oversimplified. There could be some flow to some of these ices. Some of the materials may form a kind of a more sludgy, plasticky type material. The methane ices aren't always as hard, whereas water ice gets very rigid. So there could be a little bit of stuff there, but it's pretty well a little more normal scenario than our metallic hydrogen interiors of Jupiter and Saturn for sure. And once we get to the upper part of their atmosphere, again, the elbow is about kind of the top of the cloud layers. Uranus and Neptune both have methane, which is Ch4 there. That's really the blue that we're seeing. So all the blue that dominates there, it's methane gas and methane ice crystals that have formed to make these cloud layers. And then you have other hydrocarbon ices, whether it's water or whatnot. They do have these different cloud layers, but really, like I say, we're only seeing the blue ones. And just like Jupiter and Saturn, the temperature does increase as you get further down. So there is some residual heat inside there, and as you get further down into the below the initial cloud layers, the temperature does increase. Now, on Neptune in particular, this effect does happen on both planets. Neptune, we have a lot more images of this. The Voyager 2 took some nice images of these clouds. So these pictures are taken in the late 80s, basically, of Neptune close up. You can see that there is these extra cloud layers of white clouds. They're just methane in kind of a different state higher up. You get a little more scattering of light through them, and they're above the main layer. And Neptune is thought to have more active kind of weather and more changes like this. These white layers, these white clouds, they come and go. The Neptune's going to have more active weather for two reasons. One, it's colder because it's further away from the sun, dramatically further away from the sun than Uranus is. And so this extra distance from the sun, it's much colder. So even at the top layer, you're still looking at temperatures that are 10, 20, 30 Kelvin colder on Neptune than on Uranus. And what this does is it creates a larger difference of temperature from the surface to the interior of the planet. And you couple this with, we think there's actually a little bit more residual heat in Neptune for whatever reason. There could have been some extra material there. It is just that touch more massive. So maybe it's retaining some extra energy there. But this creates a little bit of a flow of the gases. It's not dramatic. It's not like boiling out. These aren't volcanoes. This isn't some massive exchange, but there is some heat that is making its way from the interior of Neptune and making its way to the surface, and it manifests itself in these weather patterns and these clouds. And so as this heat churns up in a convective cycle where you get the hotter material rising, or the material that's not as cold rising, and it can create some areas where maybe you get a little bit of a spurt, where you get some clouds out of it. So you get these extrusions of gases sometimes that makes the surface a little bit less consistent. Uranus doesn't have these as much. In part, it's thought to have a little bit less latent heat. So there isn't as much extra energy on the inside. Plus the surface doesn't get as cold because Uranus is a little bit closer to the sun than Uranus is. But Uranus does have its own weather patterns that are probably a little bit more seasonal. So Neptune's pretty well straight up and down. It has a little bit of a tilt to it. Whereas Uranus is notable because it is actually on its side. Whereas most planets, they're pretty well straight up. I mean, Earth, a bunch of other planets have 20-ish degree axial tilts, not anything too crazy. Whereas Uranus is on its side. The axis of rotation at times actually points directly at the sun, and it lays entirely in the plane of its orbit. So the Uranus tends to have kind of some extreme seasons, which actually tends to shift the gases and kind of maybe help normalize the gas a little bit on each side, because both the south and the north of Uranus will get kind of the same effects over time. So you get a little bit of normalization. It kind of gets cooked through, if you want, or gets turned on its side. So all different sides of Uranus actually get sun exposure throughout the year, or throughout the year of Uranus in its orbit. And so this helps to heat it through, so you don't get as much big differences in the surface temperature. So these two ice giants, or just the outer two of the giant planets, are certainly notable for their blue appearance due to all this methane. Neither one of them were known in antiquity, and Neptune was predicted to have been in its orbit when we discovered it, and Uranus is on its side.